All right, standing waves. These, follow on from the pulses. I'm going to use a guitar string as our, or a violin string, whatever, as our example. When we pluck that, we get pulses running up and down here. The wave vibrates. And what happens is you get one wave, and you can do this on a string, and you can get the standing wave, or you could just attach this to a wall. You get your pulse going up like that, and you get your inverted. And you'll notice that you get certain patterns that you can get. You get the pattern where you can make it go like this, and it's just bouncing up and down backwards between these two modes. And you get the next pattern up, where you can get that sort of thing happening. And you get the next pattern up, I think you know where we're going with this, where, about there actually, you've got to sort of break it up into thirds for the next one. So you sort of go like that. And what's happening as these waves are traveling up and down, basically that one goes up and down, that one goes up and down, and that one goes up and down. And if you could stop time, as this one comes down, this one goes up, and this one comes down. And in the in-between part, you've just got a straight line, a straight wire, with nothing on it. So it's important to get an idea what's happening. And so in between, because it's all happening at once, you get nothing on the wire. That's something I didn't notice when when my physics teacher first showed it to me. But what's actually happening, even level 2s, level 3s find it hard to describe standing waves. What you've actually got is, this just looks like the wire's doing this, right? When it's got the standing wave on it. Or the other one, just doing like this. Or like this. It's not. What you've got, that's just optically what it looks like. What you've got is two waves. You've got a wave going that way and a wave going that way. The waves have the same wavelength, same frequency, same amplitude, and of course same speed. So they're exactly the same, and what they're doing is they're going backwards and forwards, and they're interfering with each other. So in reality, you have a wave on that wire, and it doesn't look like this, because that's the interference pattern. What it looks like, okay, with this one, we'll use this one as an example. This one, the wave has a wavelength of 2/3 the length, if this is the length. You can see that because you're used to looking at wavelengths. So it's got a wavelength of 2/3 that. So if we were able to stop time, and again this is our length, we would have, sure we would have this. But this wave is traveling up and down. And you've got another one exactly the same traveling back that way. And so they're forever doing this. So they actually are traveling very fast. There is this movement going like this. But because of the length and the way they fit in to the length, right, they're always cancelling out at these points here, which we call nodes. And there's these other places where at certain times they totally cancel out at the same time. That's why you've got at certain times the whole line, there's nothing on it. But there's the opposite times, which is what I've drawn, where you've got, at that particular time, you've got total constructive interference where they are adding, and so you get this increased amplitude, which is actually, if this was one wave's amplitude, you actually end up with a wave that has twice the amplitude at that particular time, because it's the interference of these two waves. So these points are called antinodes. So when you describe the wave, standing wave, talk about same wavelength, same amplitude, same speed, going in opposite directions, don't forget opposite directions, interfering with each other, constructively and destructively, to create that interference pattern we call a standing wave. Now, you can have standing waves on a violin string, just like I showed. You can have standing waves in an open tube. Now, in an open tube, you can only have an antinode at the end and an antinode at the end. You can have standing waves in a closed tube, since you can't really move backwards and forwards here. Remember, in these guys, our medium is air. In these guys, our medium was the string, right? So, these guys, that would be a node, and that would be an antinode. So what you find is that the wavelength of the standing wave is dependent very much on the length. Only certain waves can fit into those lengths. And so, let me talk just a little bit about that. With the violin, the first one that can fit in that length is a wave that looks like that. So that is half a wavelength. The next one that can fit in looks like that. So half a wavelength equaled L there, but in this case, one wavelength equals L. So because of that, this wave has twice the frequency of this one. Then we had the third one where we had 3/2 wavelengths equal L. Now you get a very similar pattern for the open air column with half a wavelength. The one that's a bit different is the closed column, where you actually start with a quarter wavelength fitting into this length. And then the next one is you add half of that, so it actually ends up becoming 3/4 wavelengths equal L, and then 5/4 wavelengths equal L. So that one's a little bit different, but you can see the main thing I want to get you to get out of this at level 2 is that the length determines the wavelengths that will constructively and destructively interfere in that situation to cause that standing wave. Now, I think we've done well with that, but one thing I wanted to say, this is a point of often confusion. When you have a wave sitting on a string, say a violin string again, and I've said that in this case, this harmonic, this is not the fundamental. The smallest wavelength or the biggest wavelength is the first one. So that's the first harmonic. And the next one up is the second harmonic, twice the frequency. The third one would be 3 times the frequency of the first harmonic. What I wanted to say here though is, so the wavelength, let's forget this one here. The wavelength equals L for the second harmonic. Now, if I want to know the frequency, okay, I can use my relationship V equals wavelength times frequency. So if I listen to the frequency, I can get the frequency, right? Because these guys are going backwards and forwards, and they are generating sound waves. So I could measure the frequency with a oscilloscope or something. I get the frequency, I know the wavelength, I can just measure it with a ruler. So I can get the velocity of the wave along the string, right? Now, what you've got to remember is that the wavelength of the string that you can measure with a ruler is not the wavelength of the sound in the air. The frequencies are the same, but the wave that travels on the string has a velocity that depends on the string. Whereas the wavelength in the air, we have the same relationship, same frequency, but we have a different wavelength because the speed in the air is different than the speed on the string. So don't get confused with that. Alright, that's enough.